Hello everyone, and thanks for attending this presentation titled as A Directional Microcrack Damage Theory for Rate-Dependent Deformation and Failure of Brittle Rocks. For underground excavations, the deformation and then the long-term stability of these structures is highly dependent on the deformation of the surrounding rock mass with time. For example, in case of tunnel excavation, the convergence of the tunnel face and also the support pressure is dependent on the time-dependent creep of the surrounding rock mass. For brittle rocks, this creep and the time-dependent behavior is well understood as a consequence of the subcritical growth of microcracks present in the rock mass. And it is not just the time-dependent behavior, but the other mechanical properties of these brittle rocks, such as low stiffness in the low stress region and also increased hydraulic conductivity near the excavation zone, are also tightly linked to the presence of microcracks. Therefore, to better understand the mechanical behavior of brittle rocks, it is important to understand and characterize the distribution of microcracks in those rocks with good accuracy. For brittle rocks, these distributions can be pretty sophisticated for both natural cracks and then the induced cracks because of applied loading. In traditional continuum damage mechanics, this anisotropy of the microcrack distribution is represented through damage tensors. But the damage tensor are limited to representing regular shapes of the microcrack distribution density, and even in some cases it can lead to or it can produce regions of negative crack density, which is not physical. Therefore, in this study, we have attempted to directly incorporate this microcrack distribution density in the continuum damage model. To do that, we first take a look at the strain induced by microcracks in a linear elastic REV. So for a linear elastic REV, the contribution from the microcracks can be computed by knowing the crack opening displacement of these microcracks. For simplicity, we start with a 2D REV in plane strain conditions with a single microcrack of size 2a and orientation omega. It is useful to define a local coordinate system which is aligned with the crack so that the coordinate x1 prime is parallel to the crack and then the coordinate x2 prime is perpendicular to the crack. And in rest of the presentation, we will use the prime notation to denote the local frame aligned with the crack. So using this change of coordinates, we can compute the strain induced by the microcrack in the REV in the local components. For an open smooth crack and loaded at the infinity or loaded by the far field stresses, this crack opening disturbances can be found using the theory of elasticity as shown. To account for the crack friction, we consider a simple stress decomposition. So in the original stress state, we have the far field stresses and we have the normal stress on the crack face, which is equals to the far field stress, and we also have a shear stress generated because of the frictional effects between the microcrack faces. In the stress state 1, we see that this stress state does not contribute to the sliding of the microcrack. In the stress state 2, however, if we increase the far field shear stress by a small amount, the frictional shear will resist it by increasing it by the same amount. However, once the frictional stress is mobilized to its limit, it cannot be mobilized anymore, and then the crack will start to slide. Considering this, we can obtain the crack opening displacement for the frictional crack by replacing tau by tau minus tau f in the case of the open crack. For the crack opening displacement normal to the crack direction, we have two things that we need to consider. First is the closing of previously open microcrack, which we have considered through the crack closing stress sigma c. So before the normal stress on the crack face is less than sigma c, the crack will be open and it will close as the stress increases, contributing to the strain. However, once the normal stress crosses the value sigma c, the crack will be closed and it won't contribute to the strain anymore. The second thing we consider is the opening of the microcracks because of dilation through the sliding of microcrack faces because of the rough shape of the microcracks, and that is incorporated through a simple sawtooth type of dilation model. Using this to crack opening displacements with the equation on the previous slide, we can derive the stress-strain relationship for the REV with a single microcrack. And further, we can integrate this with respect to stress to get the Gibbs free energy of the REV with a single microcrack, considering a zero value of the reference Gibbs free energy. Now, having calculated or having computed the stress strain relationship and the Gibbs free energy for the microcrack of the REV with a single microcrack, we move on to the REV with multiple microcracks. So here we start by considering a REV with many microcracks. And the distribution of the microcrack in this REV can be expressed using a microcrack distribution density function, which is a function of the directions omega and the sizes A. So it represents how the microcracks are distributed over different directions and sizes. And it is a normalized density function so that the total value of the integration over all the sizes and the directions is 1. Therefore, if the total number of microcracks in the REV is n, the number of microcracks between a direction omega to d omega plus d omega and a size a to a plus dA will be equal to this equation. Using this, we can compute the Gibbs free energy of the REV with many microcracks through the non-interacting homogenization scheme. In this scheme, all the cracks are assumed to be not interacting with each other so that the total contribution from all the cracks can be computed by adding up the contribution of each crack. And in case of the continuous microcrack distribution, this becomes an integration. So as we can see here, each term contributed by the microcrack has two integrals. The inner integral collects all the effects from all the sizes of the microcracks in a given direction omega, and the outer integral collects all such effects for all the directions. Therefore, it is natural to define the inner integral as the directional damage in our theory. Furthermore, here we assume that the crack closing effect is only contributed by the pre-existing natural cracks. So for the crack closing effect, we consider the initial microcrack density distribution. Using this definition of directional damage, the Gibbs free energy of the multi-crack system can be written in a more compact form, where G1 is the contribution from the uncracked REV, and then G2 represents the contribution of microcracks in the direction omega, so that integrating it over 0 to pi gives the contribution from all the microcracks in the REV. It should be noted, however, that G, or the Gibbs free energy, is not a function, but it's a functional, since it is a function of functions, since tau f, epsilon d, and the directional damage are defined for directions omega ranging from 0 to pi. So using the hyperelastic relationship on the Gibbs free energy, we can derive the stress strain relationship for our multi-cracked REV. Here, gamma f is the sliding induced shear strain contribution. Epsilon d is the dilation induced normal strain because of the sawtooth kind of motion of the microcrack. And epsilon n is the strain induced or strain contributed by the closing of previously open microcrack. The shearing induced strain is represented by the Moore-Coulomb kind of friction criteria, so that tau f here is basically the actual mobilized frictional stress on the microcrack, and tau f say is the limiting value of the mobilized friction, which is given by the friction coefficient times the normal stress on the microcrack. So from here, at any given time, the directions undergoing frictional sliding are collected in the set theta f using the yield and the consistency conditions. And from here, the evolution of the friction-induced sliding shear strain can be computed. The dilation-induced normal strain is computed using the simple sawtooth kind of dilation model, where beta governs the amount of crack opening in the normal direction due to the sliding of the crack in the shear direction. And epsilon n is actually fully elastic in nature, so it can be directly computed from the stress increment. Here, the evaluation of directional damage is inspired from the subcritical growth of microcracks, so that here the driving force for damage, the damage stress, is obtained as the release rate of Gibbs free energy with increase in the directional damage. The resistance to damage kappa is considered to be first increasing as the damage increases and then decreasing as the microcrack damage exceeds a critical value DC, and then the kappa reaches its maximum value kappa C, and then it kind of increases after that. Similar to the frictional sliding, the directions undergoing damage evaluation at any given time are collected in a set theta d, and this completes the model formulation. To evaluate the model performance, we consider an initially isotropic material such that the distribution of kappa and d are considered constant with respect to the direction at the beginning. We take a look at a typical stress strain curve for a constant state rate biaxial compression produced by the model. And then here we can see that initially the stiffness is low as the microcrack starts to close, but then after most of the microcracks are closed, the stiffness resembles very similar to the elastic response. And that is true till the onset of damage. And once the damage starts to evolve, we get the non-linear behavior. At a typical point right after the damage onset, we can see that there are some directions that are undergoing frictional sliding, but there are other directions that are not undergoing any sliding. Similarly, there are directions with damage evolution and there are directions with no damage evolution. And it should be noted that the maximum damage growth happens along a direction which is similar to the direction of failure in Moore Coulomb criteria for axisymmetric loading. To see the effect of different strain rates, we consider the simulation of the model at different strain rates. And as we can see, before the onset of damage, the strain rate does not affect the response, but after the onset of damage, the higher the strain rate, the higher will be the stiffness and the strength of the rock. To take a better look at the model performance, we use it to simulate the mechanical behavior of Mount Etna basalt from EPTL 2011. Here, as you can see, the model does a decent job of simulating the triaxial compression response in constant strain rate test at different confining stresses. Also, for the brittle creep test, we can see that the model does a good job of simulating the creep strain rate at various confining pressures and differential stresses. Similarly, the time to failure curve at a given confining stress is predicted pretty well for the Mount Etna basalt. Here we take a look at one of the strain versus time responses in the simulation of the creep and also the experimental data from VPT and all. Here we take a closer look at the distribution of the internal state functions, namely tau f, the damage stress, the directional damage, and the various strain components. So at the beginning of the creep, the distribution of these functions are shown. And because in creep we have a constant stress applied, the tau f, the damage stress chi d, and the normal stress due to crack closing will not change with time. However, in the primary and the secondary creep phase, we see that kappa keeps on increasing with time as the directional damage increases softly, so that the increase in kappa is not very rapid, and then that gives rise to the constant strain rate, and then the gamma f and epsilon d increase by the proportional amounts. However, in the tertiary creep, gamma kappa starts to decrease, and then damage blows up in a localized fashion, giving rise to the failure. To conclude, the directional distribution enables accurate capturing of the microcrack distribution without the limitations of the tensorial approximations. Also, using and building the model from a micromechanical basis allows us to incorporate different phenomena at the crack displacement at the macro level to simulate the behavior of rocks at the macro scale. Also, it is shown from the simulations that the model can capture the behavior of Mount Etna basalt in a variety and range of loading conditions with only 10 physically meaningful parameters and in initial values of 2 internal state functions. Here are the references used in this presentation. Thank you very much. I look forward to any questions and discussions in the live sessions.